Hello, this is John Miyares, and in this lesson, we're going to be getting into the meat of the course where we will focus on the study of trigonometry. Now, the roots of the word trigonometry come from the Greek trigonon and metron, which literally mean triangle measure. And for this first unit, we're going to be looking at trigonometry as it ties to triangles. Then we're going to expand our definition of an angle to look at trigonometric functions associated with angles outside of triangles. Our study is going to take us through chapters 5, 6, and 7, but not necessarily in that order. Some of you may be wondering again why I'm not teaching something in the order that the textbook has written it. Well, the textbook authors even freely admit in the forwards of their book that a lot of what is in these sections can be taught in several different orders. So the order that I'm going to choose is an order that looks first at triangles, which for some of you may actually be review of material taught in previous classes in high school. We should already be familiar with the Pythagorean relationship in right triangles, that being that the sum of the squares of the lengths of the legs of any right triangle will equal the square of the length of the hypotenuse, which more simply put is written as a squared plus b squared equals c squared, where a and b are the measures of the two legs of a right triangle and c is the length of the hypotenuse. We should also recall from geometry that if two triangles are similar, then their side lengths are going to be proportional, meaning that if we had two triangles with the same corresponding angle measures, like a 40-degree, 50-degree, and 90-degree angle, then the ratios of the lengths of the hypotenuses would always be proportional to the ratio of the lengths comparing any of the corresponding sides. What we haven't really discussed is that in right triangles, or in fact in any triangle, there will be a relationship that ties together the side lengths with the measures of the angles opposite them. So for our purposes moving forward, we're going to look at this right triangle that is marked below, and we see that the angle at the bottom left has a funny symbol to it that looks like a circle with a horizontal line through it. This is a Greek letter and it's called theta, Theta, theta. And we're going to look at this angle with the Greek letter marked theta here as a kind of reference angle by which we're going to define the positions of the three sides. The side directly across from angle theta is going to be called the opposite side or the opposite leg, for which this triangle is going to be measuring the height of the triangle, and we might call side A. The two sides that come together to form angle theta are called the hypotenuse, which is the long side of the triangle, or side C, and the adjacent leg, which is marked as side B, or the base of this triangle. Now, the word adjacent implies next to, and you might think to yourself that both the hypotenuse and the base are next to angle theta, but to distinguish them, the hypotenuse will always be across from the right angle, and the adjacent side will always be one of the legs of a right triangle. Eventually, we're going to talk about plotting triangles like this on a Cartesian plane, which will make the opposite side have height y and the adjacent side have length x, and the hypotenuse will have length r, which will represent the radius of a circle that we might set this triangle in. We're not ready for that yet, so for now, we can still just call them sides A, B, and C. Now, what we're going to do is define what I call the three primary trigonometric ratios associated with angle theta. Now, going back to our work in chapter 14, you might be asked the question, how many ways are there to grab any two sides of the triangle to turn into a ratio? Well, if there are three sides that can be used in the numerator and two different sides that could be used in the denominator, we would have 3 times 2 equals 6. If order didn't matter, we could divide that result by 2 to get 3 answers. But for the most part, order will matter. But what happens is that 3 of the results are reciprocals of the other ones. The three primary ratios are the ones that generally have dedicated buttons on their calculators, while the other three do not. The first one we're going to introduce is called the sine of angle theta, denoted with this SIN and then the symbol for the Greek letter theta. And that will be the ratio of the opposite leg to the hypotenuse of the triangle, or in this triangle diagram here, side A over side C. The cosine of angle theta, denoted COS with a theta, is the ratio of the adjacent leg to the hypotenuse, or in this triangle, side B over side C. The tangent of angle theta, denoted TAN theta, is the ratio of the opposite leg to the adjacent leg, or in this triangle, side A over side B. Now, the specification of the angle as part of this expression is important for two reasons. First, if we were looking at the other acute angle in the triangle that is not angle theta, the perspective of which side is the opposite and which side is the adjacent is going to be different compared to the perspective of the sides with respect to angle theta. Secondly, we're going to be exploring these trigonometric ratios as functions. And in a function, you have to take f of something. So just like you have to take the square root of something or a logarithm of something, a function is always going to need an argument to be a placeholder for those domain values. Now, these three trigonometric ratios and their relationships to the different sides of the triangle are going to have to be memorized, but there is an anagram that can be used to help remember what those sides are. And that expression looks like this: SOHCAHTOA. And it was pronounced SOHCAHTOA. Now, some people can look at this and say, SOHCAHTOA, what is that? Is that Sacagawea's cousin? No. SOHCAHTOA are the letters of the words that help define the ratio of the sides in the three trig ratios. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. The three secondary trigonometric ratios are just the reciprocals of the three primary ratios. The cotangent of angle theta, denoted COT with a theta, is the ratio of the adjacent leg over the opposite leg, which in this triangle is B over A. It can also be looked at as the reciprocal of the tangent of angle theta. The secant of angle theta, denoted SEC theta, is the ratio of the hypotenuse to the adjacent side, or C over B. Based on its setup, you can see that it represents the reciprocal of the cosine. Finally, the cosecant of angle theta, denoted CSC with a theta, is the ratio of the hypotenuse of the triangle to the length of the opposite side, which could also be looked at as the reciprocal of the sine of angle theta. Let's look at an example as to how we might use these ratios. Here's a right triangle with side A equals 4, side B equals 3, and side C is unknown. We are asked to find the values of the 6 trigonometric ratios associated with angle theta in this triangle. Before we can do this successfully, we need to know the measure of the length of the hypotenuse of the triangle. Since that's not given, in order to obtain it, we're going to have to use the Pythagorean theorem. So we'll set up the standard equation a squared plus b squared equals c squared and substitute in what we know: a equals 4, b equals 3. So that gives us 4 squared plus 3 squared, which is 16 plus 9, equals c squared. So simplifying the left side gives us c squared equals 25, and taking the square root of that gives us c equals 5. So the hypotenuse of this triangle has length 5. This is what we call a 3, 4, 5 triangle, And that relationship in this triangle is a special one. We call the numbers 3, 4, and 5 a Pythagorean triple because those three numbers happen to fit the Pythagorean theorem perfectly. Other examples might be multiples of 3, 4, 5, like 6, 8, and 10, or 9, 12, and 15. But there's a few others that are less obvious, like 5, 12, 13, 8, 15, 17, and 7, 24, 25. Anyway, back to this problem. The sine of the angle, according to SOHCAHTOA, is the ratio of the opposite side to the hypotenuse. The opposite side, b, equals 3, and the hypotenuse is 5. So the sine of angle theta is going to be 3/5. The cosine of angle theta is going to be the adjacent side over the hypotenuse, which in this triangle is going to be side A, which is 4, over side C, which is 5, and that will reduce to 4/5. The tangent of angle theta will be the ratio of the opposite side to the adjacent side, which will be B over A, or 3/4. The cotangent, we said, was going to be the reciprocal of the tangent, or the adjacent over the opposite, so that will give us 4/3. The secant of angle theta will be the reciprocal of the cosine of angle theta, hypotenuse over adjacent, so that will become 5/4. And the cosecant of theta is going to be the reciprocal of the sine of theta, which becomes 5/3. Now, a common mistake made between these is that people mix up which secondary ratio goes with which primary ratio. Folks that think the sine goes with the secant and cosine should go with cosecant, but that's not the case. In this one, the ratios that begin with the letter S are always matched with ones that begin with the letter C. So sine goes with cosecant and cosine goes with secant. Here I'm just going to show that we can see if as long as I put these in this order, sine, cosine, tangent, cotangent, secant, cosecant, that I can match these trig ratios up like so, and they'll be, you know, the ones that match with each other are essentially mirror images with each other. Here's one to try on your own. Evaluate the following based on the triangle given. Now, in this one, you might be thinking we flipped the theta sign sideways, or that maybe we're using the symbol for a null set here. But this is actually a different Greek letter. This is the Greek letter phi, spelled Phi, but pronounced phi. Sometimes this letter is pronounced phi in the Greek language, but I'm not here to teach you all Greek, but just some of the Greek letters that we're going to be using for symbolism in this course. The most common Greek letters we're going to be labeling angles with are going to be theta and phi, but we may also use alpha, beta, and gamma, which I'll show you on another slide. Anyway, why don't you pause this video for a minute or two and try to do this one on your own? You have side A, which is 4, side C, which is 6, and at this time, side B is unknown, so you'll first need to figure out what side B is using the Pythagorean theorem, and you will want to get this in simplified radical form before evaluating the trig ratios, and then you can evaluate the 6 trig ratios. All right, so the Pythagorean theorem gives us 4 squared plus b squared equals 6 squared, or 16 plus b squared equals 36. Moving that to the other side, you get b squared equals 20, which means b is the square root of 20, which reduces to 2 square roots of 5. Setting up the trig ratios, you've got the sine of phi, which is 2 root 5 over 6, that reduces to root 5 over 3. The cosine of phi, adjacent over hypotenuse, is 4/6, or 2/3. The tangent of phi is going to be 2 root 5 over 4, which reduces to the square root of 5 over 2. The cotangent of phi is the reciprocal of the tangent, which will give 4 over 2 root 5, which we will want to rationalize by multiplying the top and bottom by the square root of 5. This gives 4 root 5 over 10, which reduces to 2 root 5 over 5. The secant is the reciprocal of the cosine, which will just be 3 halves. And the cosecant will be the reciprocal of the sine, which becomes 6 over 2 root 5, which rationalizes to 6 root 5 over 10, reducing to 3 root 5 over 5. How are angles measured? The most common way that you're probably aware of from your previous studies is to measure them in degrees as a decimal, like 24.81 degrees. There are 90 degrees in a right triangle, 180 degrees total if you add up the measures of any three angles in a triangle on a flat planar surface, and 360 degrees making up a full circle. Angles can also be measured in degree minutes seconds form, and many latitude longitudinal maps are based on this particular structure. The idea is that there are 60 minutes in a degree and 60 seconds in an hour, similar to what you will have seen as a measurement of time. Our calculators do have a feature which will allow us to convert decimal degrees to degree minutes seconds, and I can show you that at a later time. The third way that these are measured is in something called radians, and radians are about as different to degrees as centimeters are to inches, but I will say they're not metric. We will discuss them soon enough, but for now, let's get comfortable with measuring angles in degrees. Before we get too far, I thought I would post on here for reference in case you see the various Greek lettering and assignments and notes in the future. The ones you will probably see the most in mathematics are going to be the ones that are shown here, but by no means is this all of them. There are 24 letters in the Greek alphabet, starting with alpha and going on to beta and so on. That's why they call it the alphabet. That came from the Greeks, where we might have you recite your ABCs in elementary schools. In the Greeks, you were reciting your alpha, beta, gammas, or alphabet for short. Now, as with the English language, there are some letters that are capital letters and others that are lowercase letters. In some cases, they look very much the same, but in other letters, like delta or omega, the uppercase and the lowercase are very much different. This table is also in the handout notes packet as well. Now, sometimes you're going to hear me refer to these trigonometric ratios as trigonometric functions. And in some ways, you might think that I'm using the terminology interchangeably, but these trigonometric ratios really are functions. In any function, you have a domain, you have a range, and a rule that helps you define how to get from the domain to the range. The domain of these six trigonometric functions are the angles. The range values are the ratios of those different side lengths compared to each other. Most of these ratios can be evaluated on the calculator. So if you were given questions like these where you're asked, what is the sine of 24 degrees or the cosine of 38 degrees or the tangent of 53 degrees, these are simply one button type problems to do on your calculators. Unlike when I was in high school, we had to look these values up in what are called trigonometric tables in the back of our textbook. So I'm going to switch gears here and turn on a calculator emulator for a second that I can share with you. All right, here's basically what a TI-84 is going to look like. On the left side, you're seeing an example of the keyboard. On the right-hand side, you're seeing my screen. When doing these trigonometric problems, you're going to first have to make sure you're in the right mode. So we're going to press the mode button here. And let's look at our options. You see a line that says radian degree. By default, the calculator is set up to work in radian mode, but for our purposes in this unit, we're going to be calculating our angle measurements in degrees. So let's switch this up to degree mode by highlighting the word degree and then clicking enter. Once we have this set now into degree mode, we can now quit or hit clear. I'm going to hit second function, quit, in order to go back to our home screen. To evaluate the sine of 24 degrees, I can just hit sine and then hit 2 and 4, and then I can just hit enter and it will evaluate a decimal for us. For cosine of 38, we can press COS 3, 8, and we can close the parentheses. You notice when you hit the cosine, sine, and tangent buttons, you're going to get a left-hand parentheses automatically inserted there. If all you're doing is evaluating the trigonometric ratio, you do not need to close it. However, if we start doing work where you're going to be combining the cosine of 38 with some other computation, you will need to close the parentheses so that we can maintain the proper order of operations. But if you're just evaluating like the tangent of 53 degrees, you don't need to necessarily close the parentheses. Now, if you weren't sure what mode you were in, what option that you have is to insert a degree symbol after typing up your expression. And we can get to that little angle symbol by going to the angle menu, which is second function apps. So to show as an example, I'm going to reevaluate the tangent of 53 degrees, but I'll type tan 5, 3, then I'm going to hit second function, apps, and you're going to see option 1 has a little degree circle. Option 2 has a little apostrophe, which we will use to describe the minutes. And option 4 says DMS, which will allow us to convert our decimal to degree minutes seconds. I'll show you that in a second. And then we have this letter R, which will allow us to make sure we're in radians. By selecting option 1 here, and then closing our parentheses, it will know I want to take the tangent of 53 degrees, and that will override the calculator's choice of what mode we're in. So if we were in radian mode and I told it the tangent of 53 degrees with a degree symbol, it will calculate things properly. Whereas if I said, what is the tangent of 53 radians? And I will go through here, say second function, angle, and then hit a 3, close my parentheses, we'll get a very different answer. Now, let's say I wanted to convert an angle measurement that was in decimal degrees into degree minutes seconds. What I could do is say 24.81 degrees, and then I'm going to go to my angle menu, second function apps, and I'm going to choose option 4, which I can either click by doing the number 4, or I can click the down arrow 3 times to choose DMS. And what that will then show me is that 24.81 degrees becomes 24 degrees, 48 minutes, and 36 seconds. And there you have it. So going back to our slideshow here are the 3 values that we just calculated. Typically, when you're recording your answer, you want to go at least 4 decimal places, maybe 5. Of course, if you're doing computations on the calculator, you saw that the calculator was giving you a lot more decimals than that. There's no reason why we can't try to keep all of them. On your WebAssign homework, be mindful as to how many decimal places they want you to record your answers to. So here's a few that you can try on your own. You should probably pause for a minute to see how well you can do these on your calculator. All right, assuming that you've had a chance to do this on your own, here are the answers for these. Now, Hopefully, something that you notice is that the sine of 30 degrees is the same as the cosine of 60 degrees. Similarly, if you were to look back at the previous screen, you'd see that the value of the sine of 52 degrees is the same as the cosine of 38 degrees, or even that the sine of 24 degrees is the same as the cosine of 66 degrees. This has to do with the nature of the triangles in question. Those particular angles are called complements to each other, and the two angles are considered complementary if their sum is 90 degrees. This might make more sense if I try drawing a picture of what this is going to look like. So I'm going to try using this free-handed draw tool here, and I'm going to construct a triangle like so. And I'm going to mark the angles in the corners here and here. And I'm going to mark this one as angle phi, and I'm going to mark this one as angle theta. And I'll mark this side, I'll just call that A. I'll call this one B, and I'll call this third side C. Now, for right triangles, what happens here is that you have a right angle in the corner, and then we have these two other acute angles that have to be complementary to each other. If there's 180 degrees in the triangle altogether, then this right angle takes up 90 of them. These other two acute angles have to account for the other two 90 degrees. Let's say I label the three sides as you see here with A, B, and C, like you would expect them to be labeled. In one corner, we have angle theta. This might be a 30-degree angle. In the other corner, you have its complement. This would have to be a 60-degree angle, or vice versa. We could say that angle theta is a 38-degree angle and angle phi is a 52-degree angle, or angle theta is 22 degrees, angle phi is 68 degrees. If you look carefully at this triangle, the sine of this smaller angle theta is going to be the opposite side over the hypotenuse, which is going to be A over C. Whereas with the larger acute angle, if I look at the cosine, it also will be A over C. One angle's opposite side here is going to be the same as the adjacent side to its complement. So therefore, you're going to see that the sine of one angle will equal the cosine of its complement. A similar relationship can be found with tangent and cotangent, where the tangent of angle theta will be A over B, and the cotangent of angle phi will also be adjacent over opposite A over B. Let's talk about how we're going to calculate the secant and cosecant of angles like these shown here on this slide. To do that, we're going to have to switch back to our calculator. The secant is the reciprocal of the cosine. And to take the reciprocal of something is to take 1 over it. So what we're going to want to do is divide 1 over the cosine of 41 degrees if I want to calculate out the secant of 41 degrees. I hit enter, and there's my answer. Similarly, the cosecant of 18 degrees will be 1 over the sine of 18 degrees. So I'll take 1 divided by sine 18 and hit enter. And lastly, if I want the cotangent of 65 degrees, I'll say 1 divided by tangent 65 and close my parentheses. Now you'll see here up above the buttons sine, cosine, and tangent, you'll see up here it says what looks like sine minus 1, cosine minus 1, tangent minus 1. And your first thought might be, why can't I use those buttons to calculate the reciprocal? After all, that minus 1 usually means reciprocal, right? Wrong. These are actually going to be the inverse sine and the inverse cosine functions. And we're going to talk about them before we get to the end of this video. But what I'm going to warn you is if you try to use them in a problem like this, say you want to take the inverse cosine of 41, thinking what you were doing was the reciprocal of the cosine of 41, what you're going to see here is that you're going to get an error, a domain error, which hopefully will be a sign that you're not doing something correctly. Long story short, there is a difference between the reciprocal and the inverse of a trig function. So let's go back to our slideshow. So as we mentioned before, to calculate the secant of 41 degrees, we're going to take the reciprocal of the cosine of 41 degrees to get 1.325. The cosecant of 18 degrees is the reciprocal of the sine of 18 degrees, which will be approximately 3.236. And the cotangent of 65 degrees will be the reciprocal of the tangent of 65 degrees, which gives you 0.4663. Why don't you try the next three on your own to make sure you get the hang of this? When working on these, you probably want to round the number of decimals to either at least 3 places, more often 4 or 5 places. And again, if we're doing the work on our calculators, we'll often keep all the decimals they give us. In most cases, the values are going to be irrational anyway, so we won't need to worry about trying to turn them into fractions at all. Go ahead and pause this video and see what you come up with. So since we still have a ways to go in this lesson, I'm not going to spend too much time on these. So here's what you should have come up with the secant of 72 degrees, the cotangent of 37 degrees, and the cosecant of 49 degrees. For acute angles, there is going to be a one-to-one relationship between the size of the angle and any one of the associated trig ratios. That can be interpreted in multiple ways. When we talk about one-to-one functions, you have a function that not only for each x do you have only one y, but you also for each y value have only one x. So for example, the sine of any angle will be unique for any acute angle, and that value will be something between 0 and 1. The bigger the angle, the bigger the sine value. Another way you can look at this is to say, well, if I have the sine of 30 degrees equals 0.5, means in any right triangle that has a 30-degree angle in it, the ratio of the leg opposite the 30-degree angle to the hypotenuse will always be 1/2, no matter how big or how small the hypotenuse is. So if you were told here that angle theta were 30 degrees and the hypotenuse had a length of 10, then the opposite side, A, would have a length of 5, which would be half of 10. If the hypotenuse had a length of 28 and the angle theta was still 30 degrees, then the opposite side would have a length of 14, which is half of 28, in order to make the ratio of the opposite over the hypotenuse reduced to 1/2. Here are some examples that we can explore this idea to do what we call solve triangles. Suppose you're given this diagram with a 68-degree angle in the upper corner, a height of 5, a base length of x, and a hypotenuse of y, and you're asked to solve the triangle. This means that you want to determine the values of x and y in the triangle as well as the measure of the missing angle theta. Well, the missing angle is easy. It will always be the complement to the other acute angle. So you have 90 minus 68 will give you 22 degrees. You could also subtract 180 from the other two angles, and you'd have 180 minus 90 minus 68 to get 22 degrees again. Now, in order to find the side lengths, we're going to have to look at the sides we're given and the angles that we're given and pick a trigonometric ratio that relates those givens to each other. In this case, let's say I'm looking at the 68-degree angle that we're given. The 4 is the side adjacent to that angle. If I wanted to find the length of hypotenuse y, I could use a cosine ratio to say I want the cosine of 68 degrees to be equal to the adjacent side 4 over the hypotenuse y. From here, we can generate the value of the cosine of 68 degrees on our calculator to get the decimal 0.3746. Then we'll set that decimal equal to 4 over y, our adjacent over the hypotenuse. From there, we'll cross multiply to get 0.3746y equals 4, which then if we divide it out, we'll get y equals 4 divided by 0.3746, which becomes 10.678. Now, based on the nature of this triangle, we could have said we wanted to look at the sine of 22 degrees instead of the cosine of 68 degrees, and we would have gotten the same answer. However, as a rule of thumb, it is safer to work with your givens than to work with calculated values, because if you miscalculated the measure of the missing angle, let's say you subtracted from 100 instead of from 90 and got it to be a 32-degree angle instead of a 22-degree angle, you'd get a very different answer than you should, all because you used a wrong number in the beginning. You'd get what we would call the fruit of the poison tree. Now, let's say we wanted to find side x, which is opposite the 68-degree angle. With the 4 being the adjacent side, we can set up the tangent of 68 degrees, which we would have 2.475 equals x over 4. If we cross multiply that, we're going to get 9.9 equals x. Now again, you could have chosen to do the sine of 68 degrees equals x over 10.678, but again, just like before, it's better to work with a given value rather than a calculated value, just in case your calculated value is not correct. Additionally, the 10.678 length that we got for the hypotenuse is actually a rounded value. Depending upon how far we rounded, we might actually get a slightly different answer for x. Now you can check your answers by using the Pythagorean theorem. We can plug in the three sides, a squared plus b squared equals c squared, into the formula as seen. And with a little bit of rounding here, what you should see is that this is going to fit the way we expect it to. Here's another one for you to try on your own. Go ahead and pause the video for a few minutes to see if you can work this one out. You're given a base angle of 50 degrees and a hypotenuse of 10. You want to find the length of the opposite side x and the adjacent side y. Set up an equation relating the trig ratio and go from there. So the missing angle will just be 40 degrees in order to make the total number of degrees add up to 180. To find side x, we're going to use the sine function and say that the sine of 50 degrees equals x, the opposite side, over 10, the hypotenuse. We can decimalize the value of the sine of 50 degrees, then cross multiply to get 7.66 equals x. For y, we're going to use the cosine to get the adjacent side y over the hypotenuse 10. We get a decimal equivalent for the cosine of 50 degrees, then multiply that by 10 in order to get y equals 6.428. We can check our answer by using the Pythagorean theorem to take x squared plus y squared. We'll add them up, and you'll see that they do add up to 100, which is 10 squared. So the hypotenuse is the square root of the 100, which is 10. Now, going back to this idea, trig ratios are functions in the sense that you have to take the sine of something or the cosine of something, just like you have to take the square root of something or the logarithm of something. I also mentioned that trig ratios are unique for a particular acute angle. So if we had a situation where we could see that the sine of some angle theta, the ratio of the opposite to the hypotenuse, reduced to 1/2, then we can go backward and figure out what unique acute angle has a sine value that would reduce to 1/2, which we've already looked at as being a 30-degree angle. This calculation can be done either on a calculator or from a trig table, but who actually looks things up in tables these days? Heck, we don't even really have books that we can look things up in these days. So let's say we're trying to find the angle in a triangle, knowing that we have the ratios or even just the side lengths. Suppose we were told that the sine of angle theta was 0.4227 and you wanted to find the measure of angle theta. This is where we're going to use the inverse sine function to go backwards on this. On a TI-83 or a TI-84, make sure you're in degree mode like I showed you before. Then we'll press the second function button, then the sine button, and then the decimal 0.4227. You can close the parentheses if you want, but you don't have to for a problem like this. And then we can hit enter. This process is called finding the inverse sine of the value, and it will tell you the angle associated with that particular ratio. All 6 trig functions have a corresponding inverse. Why don't we switch over to the calculator again and take a look at how we might do that? So here, again, we're going to verify that we're in degree mode before we continue. I hit the mode button, it says we're in degree mode, and I can hit second quit, and that will get me back to my home screen. Now, when I press the second function button and then the sine button, we're going to see that sine, the -1, come up. Again, that's not really the -1 power. It's actually going to be the inverse sine function, which is sometimes called the arc sine function. It's set up to truly be the inverse of the sine function. Remember, in sine and cosine, you plug in an angle as the domain value, and your return value in the range is going to be a ratio between 0 and 1. For the inverse sine or inverse cosine, you're going to be plugging in the ratio and getting back the angle. So remember, in an inverse function, you're going backward from y to x. So here, I could say the inverse sine of 0.4227, and I will close the parentheses, we're going to get approximately 25 degrees. We can do that for others as well. Let's say I wanted to get the inverse tangent of 1.5. I'll hit second function, tangent 1.5. I'll close my parentheses, hit enter, and I have approximately 56.3 degrees. Another one we could do, I could say, what is the inverse cosine of 1/2? I could type that in as the decimal, or I can even type this as the fraction, inverse cosine of 1/2, and that gives me 60 degrees. Now, there are some limitations here. For example, since the sine function can only generate values between 0 and 1 as range values, then the domain of the inverse sine function can only be decimals between 0 and 1. Let's say I tried taking the inverse sine of 30. It's going to give me an error because if you think about it, I'm telling the calculator to give me the measure of some angle in a right triangle where the opposite side is 30 times as long as the hypotenuse. Well, the hypotenuse is always the longest side of the triangle, so the opposite side can never be longer than the hypotenuse, much less 30 times as long as it. At most, it could approach a ratio of 1, but that would assume that the opposite side would be equal in length to the hypotenuse, which can only happen if what you have is an angle approaching 90 degrees. Here's a few to try. Determine the angle measure of phi and theta in the triangles below. This one we've worked with already in finding the missing side lengths and the ratios, but we never did look at the angles themselves. In this case, we have angle phi is our base, adjacent side is 4, and the hypotenuse is 6. What I would start out with is to say the cosine of angle phi equals the adjacent side 4 over the hypotenuse 6. From here, I want to know what angle has a cosine value of 4/6 or reduced 2/3. So I'm going to take the inverse cosine of both sides of this equation. This is the proper way that we should approach this algebraically when solving a trigonometric equation. You're always doing something to both sides of an equation when solving for a missing variable in an algebra problem. If this was x squared equals something, you'd take the square root of both sides. If this was e to the x equals something, you'd take the natural logarithm of both sides. And that's what would cause things to cancel. You can take the inverse cosine of both sides here because the inverse cosine will cancel out with the regular cosine and leave you with just phi on the left equals the inverse cosine of 4/6. Punching that into the calculator gives you phi equals 48.2 degrees. Here's another one. Why don't you try this one on your own? You want to find the measure of angle theta, and you're given that the opposite side is 3 and the adjacent side is 4. We already know the hypotenuse is 5, but we never did figure out what the angle theta was going to be. So let's pause for a minute so that you can try this one on your own. So since we're given the opposite and the adjacent, we're going to want to use the tangent ratio to get the tangent of theta equals 3/4. Again, in order to get the theta by itself, we'll want to take the inverse tangent of both sides. That will cause the tangent to cancel out on the left, which leaves us with theta equals the inverse tangent of 3/4. Running that through the calculator gives theta equals 36.87 degrees. Now I want to explore some word problems or some story problems that are tied to trigonometry. You won't have too many to deal with at the start, but we will be doing more of these as the course progresses. There will be some problems where you'll be asked about the angle of elevation, which is defined as the angle measured above the horizon, or an angle of depression, which is measured below the horizon. A third term, the subtended angle, is an angle caught between two lines of sight. Here's a diagram of that situation. We have a standing person looking up at a plane and down at a dog. The angle above the horizon, or above the horizontal line, is the angle of elevation, and the angle below the horizontal line is measured as the angle of depression. The subtended angle would be the entire angle formed between the airplane, the person's eyesight, and the dog. Here's our first example to work through. A woman is standing 140 feet away from a tree and can see the top of the tree at an angle of 20 degrees in an angle of elevation. How tall is the tree? All right, here's a diagram to explain the situation. I didn't draw in the woman here because, well, it was hard enough to get the clip art of the tree in here. So we have our tree. We have the woman standing 140 feet from the tree at the bottom corner of the triangle, and the angle of elevation of the top of the tree is marked as 20 degrees. We're interested in the height of the tree, which I've marked here with the letter H. The H is the opposite side relative to the 20-degree angle, and the 140-foot distance that we've labeled D is going to be the adjacent side to the 20-degree angle. Knowing I'm interested in solving for opposite side H and I'm given adjacent side D equals 140, we'll use the tangent ratio. Tangent of theta will be the opposite side over the adjacent side. In this problem, our angle theta is 20 degrees, so we have the tangent of 20 degrees equals h, our opposite side, over 140, our adjacent side. Cross multiplying, we can say that h equals 140 times the tangent of 20 degrees, which is going to be some decimal, but I'm not going to say that you need to write out the decimal for these trig ratios here. We can type that directly into the calculator as you see here to get h equals 50.956. Of course, story problems should be answered in whole sentences, so it's best to finish this problem by writing out in the whole sentences the tree is approximately 51 feet tall. Here's another example. A wheelchair access ramp rises 6 feet over a 20-foot length along the diagonal. What is the angle of inclination or elevation of the ramp? Well, here's our diagram showing the situation. You can see angle theta marked in the corner as the angle of elevation of this ramp. The height 6 across from angle theta is going to represent the rise in the ramp, and the 20-foot length is along the diagonal we will label with the letter L. You're interested in finding the value of angle theta, so we have the opposite side and we have the hypotenuse. That's going to be best expressed using the sine ratio. Filling in our givens, we have the sine of theta equals 6 over 20, which could reduce to 3 over 10, or 0.3. Taking the inverse sine of both sides, you're going to get the inverse sine of 6 over 20 will equal angle theta, which we can plug into the calculator and get an angle measure of approximately 17.4576 degrees. Finally, we can write out our answer as a whole sentence and say that the angle of elevation of the ramp is approximately 17.5 degrees. Pay attention in WebAssign to see what the rounding rules are going to be for your answers. This example is a bit more complicated. An observer on the 12th floor of a building determines that the angle of depression to the foot of a building across the street is 54.6 degrees, and the angle of elevation to the top of the same building is 82.3 degrees. If the street is 80 feet wide, find the height of the observed building. Here's a picture of the situation. For argument's sake, let's say our smaller building only has 12 floors on it, and so that the person doing the observation is at the top of the smaller building. We see that the two buildings are 80 feet apart, and the angles of elevation and depression are marked as seen here. The problem is that, what do we know? We can't just try to solve for the entire height of the big building in one step because there isn't a right angle right there. What we could do is split it up into two right triangles by looking at this horizontal dash line that we put across the building here and here. So we're going to label the part of the building that is across from the 82.3 degree angle as side X, and we'll label the side across from the 54.6 degree angle as side Y. Then we're going to add the values of X and Y together in order to get the total height of the building. Looking at each triangle separately, we'll first solve for X and then solve for Y. We'll have the tangent of 82.3 degrees equals X over 80. We can multiply 80 by the tangent of 82.3 degrees, then plug that in on our calculator as we cross multiply. We will get 591.69 feet. To find y, we'll say the tangent of 54.6 degrees equals y over 80. So y will equal 80 times the tangent of 54.6 degrees, which will give us 112.57. From here, we can get the entire height of the building is 704.26 feet by adding the two components together. Let's look at one more. But before I do that, let me erase that drawing from the previous slide. Suppose you're standing 30 feet away from a statue on a pedestal. The pedestal is 16 feet high. The angle subtended between the foot of the statue and the top of the statue is 30 degrees. How tall is the statue? This one is a little more complicated than the previous two. Let's try to draw a diagram here. So we have a statue of a stick figure on top of a pedestal. We know the pedestal is 16 feet high. We know someone is standing 30 feet away, and we know that the angle subtended between the foot of the statue and the top of the statue is 30 degrees right here. What we want to find is the height of the statue. The problem is that the value of h that's there isn't across from the right angle or anywhere near the right angle. The right angle, assuming we're at level ground, is going to be at the base of the pedestal. So here's our strategy. We're going to first find the measure of this angle, theta, that shows the angle of elevation from the base of the pedestal to the top of the pedestal. And then we're going to add it to the 30-degree angle that we have here in order to figure out the entire angle of elevation from the bottom of the pedestal to the top of the statue. Once we have that, we can use the tangent ratio to measure the entire opposite side, which will be h plus 16, and compare that to the adjacent side here, which is 30. Once we know the entire height, we could then subtract off the 16-foot tall pedestal in order to be left with just the height of the statue. So let's try this. We can say that the tangent of this angle theta in the corner is 16 over 30, which then theta can be found by taking the inverse tangent of 16 over 30, which gives us 28.07 degrees. That means that the entire angle of elevation to the top of the statue from ground level will be 58.07 degrees. Now we'll use this new angle to find the total height. I can say that the tangent of 58.07 degrees will be the opposite side, which is h plus 16, over 30, the adjacent side. Cross multiplying gives h plus 16 equals 30 times the tangent of 58.07. When we run that through the calculator, the left side becomes 48.145 equals h plus 16. We'll then subtract 16 from both sides to get a final answer h for the height of the statue to be 32.145 feet. So yes, that was long and that was a lot to absorb, but I wanted to try to incorporate as much as possible into the lecture here, including any anticipated questions you might have about the process, which is what made this lesson a little bit longer than normal. These trigonometric ratios, the sine, cosine, and tangent, and whatnot, are going to serve as the foundation of our studies of trigonometry for the next 3 chapters. So it's really important that we understand the ins and outs of the basics of these trig ratios before we start dealing with more complex ideas involving these trig ratios. Here's the problem challenge for this section. Some of you may want to go back and review parts of this video, or at least go back and look at the slides from this presentation again before trying the problem challenge. And that's not a bad idea. Go ahead and give these problems a try. And if you have any questions, go ahead, you can send me an email, or better yet, you can post it on the discussion board. Thanks for watching, and we'll see you all soon.